Electrohydrodynamics, EHD, is not the same as electrodynamics. The field of electrodynamics includes both EHD and MHD, so all forms of EHD propulsion and MHD propulsion are also electrodynamic propulsion, but not all forms of electrodynamic propulsion are necessarily EHD or MHD. Electrodynamic propulsion is a useful term to distinguish MHD in a conductive physical fluid from MHD type propulsion in a non-physical medium such as the quantum vacuum. Now let's move on to the next section of this video, MHD propulsion fundamentals. To begin, let us remind ourselves of how wings work. If you research the subject how wings work on your own, you will eventually discover that there is no one single answer to explain how they work. However, you will find all explanations revolve around the concept of creating a pressure differential between the top and bottom of a wing, with the aim being to increase the relative pressure on the underside of said wing, leading to an effect called lift. To clarify, the exact mechanism of lift really depends on the specific circumstances, flight environment, wing design, etc. Different mechanisms must be at work in different situations, or even multiple mechanisms may be active at the same time, or for the same wing or airfoil at different times, lower or higher speeds, etc. Now that we are finished re-examining how wings work, it is time to consider the meaning of the term Lorentz force. What is the Lorentz force? The Lorentz force is the repulsive force between magnets, or more specifically, it is a force that arises when electric current is at a right angle to a magnetic field. This occurs even for permanent magnets such as ordinary fridge magnets. In this case, the currents involved are created by the magnets themselves as opposed to being created separately, as we will discuss with regards to MHD propulsion. These currents are also generally quite weak. It is worth noting briefly that the repulsive force you feel when trying to push a pair of magnets together is in fact the Lorentz force. A fluid can be accelerated, decelerated, or its pressure increased or decreased via the Lorentz force. In order for the Lorentz force to act on a fluid, the fluid must either be conductive already or made conductive in the moment, such as by ionization or the addition of electrolytes. In the case of MHD propulsion, oppositely charged electrodes are used to create the needed electric current through the fluid. A magnetic field is then passed at a right angle to it, giving rise to the Lorentz force, accelerating or decelerating the fluid. If the fluid is already moving, a Lorentz force can be used to either accelerate the fluid further and thereby decrease its pressure, or to decelerate the fluid and so increase its pressure. If you are looking for an even more detailed description on the Lorentz force, you can easily find one on Wikipedia. We will put a link to said description in the description section of this video below. We will also leave a link to a comic book style explanation of how MHD propulsion works by Jean-Pierre Petit. Despite the comic book style, the explanations given are very accurate and thorough. Okay, so far we have covered this: what MHD propulsion is, how it works, and covered some of the fundamentals of MHD propulsion. Now let's move on to the next part of this video, how MHD propulsion functions in an atmosphere. Now remember, electric and magnetic fields can only act on a conductive medium. Therefore, to operate in an atmosphere, an MHD propelled vehicle must first ionize the air. This can be done in one of several ways, but one of the most efficient methods is known as high frequency pulse discharge, or HF pulse discharge for short. This is where an alternating current at radio to microwave frequency or higher produces electromagnetic radiation in fields that ionizes air or other gases very efficiently. The ionized air then forms a conductive sheath just off of the surface, which absorbs all or most of the emitted radiation. Once the air is ionized, it can be moved via electromagnetic forces such as the Lorentz Force or via an ion wind effect. This is where EHD propulsion, ion wind propulsion, and MHD propulsion can sometimes be confused with each other because in some vehicle designs, both forms of propulsion can be implemented on the same vehicle to maximize efficiency. Also, different versions or iterations of a vehicle might use only ion wind propulsion, only MHD propulsion, or both. The airflow created by MHD acceleration or ion wind is directed over an airfoil creating lift. This can be airfoils in the form of more or less conventional wings. Alternatively, a saucer-shaped Coanda effect airfoil provides greater lift than a conventional wing and is well suited to MHD or EHD that creates a wind without the need to move the entire vehicle nor even the airfoil. Think of the saucer airfoil as a wing wrapped around the vehicle. MHD propulsion can also come in the form of a MHD plasma jet engine with a very high power density. That is, a small device will produce very high thrust. This is in sharp contrast to ion wind thrusters, which have a very low power density and therefore typically very low thrust. MHD propulsion in space. The simplest and easiest form of MHD space propulsion are MHD jet engines, or rather MHD rocket engines. These can utilize the Lorentz force to directly accelerate a cold plasma. Alternatively, radio frequency discharge or microwaves can be used to superheat a gas into a hot plasma state, which is then kept off the walls via magnetic fields, which involves Lorentz forces. The hot plasma is then allowed to escape as with a conventional chemical rocket engine. There are advantages and disadvantages to both. Both can have a high thrust and a high efficiency. Though using a hot plasma will generally give a higher thrust but lower efficiency unless the plasma is extremely hot, as in fusion temperatures. In the not-so-distant future, we will utilize MHD space propulsion that pushes off of the quantum vacuum directly. To avoid confusion with strictly atmospheric or water-based MHD, we sometimes call this electrodynamic propulsion. Empty space is not actually empty. It is filled with extremely short-lived particles, usually called virtual particles. However, the term virtual particles is a misnomer and historical misnaming, as these particles are not fundamentally different than ordinary particles. The only difference between the so-called virtual particles and ordinary particles is lifetime. Though virtual particles are exceedingly short-lived, most things happen over very long periods of time in comparison, so the activity of the virtual particles cancels out and can be safely ignored. However, for electromagnetic fields or radiation with a very high energy, very high frequency, or both high energy and high frequency, these virtual particles cannot be ignored. Therefore, ultra-short and intense electromagnetic pulses can interact with these abundant and ubiquitous particles, particularly the short-lived electrons and anti-electrons, also known as positrons, a kind of antimatter. These ultra-short and intense electromagnetic pulses can then be used to create Lorentz forces on the electron-positron plasma, creating thrust.